Hi, thank you very much for having our paper in this conference. The name of our paper is Leader Election in Arbitrarily Connect Networks with Process Crashes and Weak Channel Reliability. This is a joint work that I did with Carlos Lopez, my advisor Sergio Raxdown, Professor Michelle Reynal. And the first thing that we need to know is about the eventual leader election problem. In this problem, every process has a local variable called leader I, and it is required that eventually the leader I forever contains the same name of some process. The algorithm must elect a new leader each time the previously elected leader crashes, and this problem is denoted as the omega failure detector, which is actually the weakest failure detector for solving the consensus problem. Now, what is this presentation about? We present an algorithm for implementing omega in arbitrarily connect networks composed of eventual ADD channels where processes might fail by crashing. Now, the first question is, what is an ADD channel? Well, an ADD channel from P to Q is formally defined as follows. For every K messages sent from P to Q, at least one is delivered within time D. The other messages can either be lost or arbitrarily delayed. In this figure, we have an example of an execution of an ADD channel. And in this case, we have K equals to 4, and every arrow from P to Q, it's a message that P sends to Q. Now, green arrow is a message that has been delivered. Blue arrow is a message that has been delivered within time D, and red arrow is a message that is lost. Now, working with ADD channels is hard, first because K and D are not known by P nor Q. We know that they exist, but P nor Q does not know which K and D we are dealing with. Second, because ADD channels are unidirectional, and every channel has its own K and D. Now, if we want to transmit something from P to Q, we need to send a message several times in order to be delivered. Again, returning to our main question, what is this presentation about? We present an algorithm for implementing omega. And the most challenging of all, now that we know what is an ADD channel, is the use of messages of order log n. And the challenge comes from the uncertainty that processes do not know neither K or D, and D, or the time at which the channel satisfy the ADD property. Now, we have several basic previous work that were our inspiration. This is the first paper is this from Chandra and Tueg, in which they proposed the unreliable failure detectors, and they proposed a technique for the use of heartbeat messages for detecting failures. And then we have this paper from Hatzilakos et al., where they define the omega failure detector. Then we have a paper from Sastry and Pike, where they proposed for the first time the ADD channels, and they gave an implementation of the failure detector Diamond P for complete networks. And then we have the paper from Kumar and Welch, where they proposed an algorithm for Diamond P for arbitrary networks of ADD channels. And then we proposed an implementation of Diamond P using messages of order of n log n, and for achieving this bound, we use an integer to encode the intensity of the message sent from some process. Now, we want to reduce the message size even further by moving from the Diamond P problem to the omega failure detector. Now, our formal model for this omega is a system that consists of n processes, and this n is known by every process, and every process has its own local clock. Processes might fail only by crashing, and we assume that there is an unknown spanning tree containing all correct processes connected by diamond channels. Diamond ADD channels, with the root being the correct process with the smallest identity. This is a necessary condition since we need the candidate to be the leader needs to be able to communicate with all the correct processes in the network. Now, the main idea of the algorithm is that each process, PI, periodically sends an alive message to all its neighbors while it is alive. And this message contains its proposal for the leader and a number that we will call the hop bound. Now, at the beginning, when the algorithm starts its execution, every process PI proposes itself as the leader and will send a message alive n-1. And in this case, n-1 is the greatest hop bound that a process can send to its neighbors. Now, what happens when a process PI receives an alive message? Well, it needs to check if J is lower than I. In that case, PI adopts J as the current leader and will save the n-k hop and starts a timer expecting this hop again. Now, the next time that PI sends live messages to every neighbor, it will send J n-k plus 1 to its neighbors, meaning that PI adopts J as a leader and will save the hop bound that it received on the previous message. Now, from this rule, we can conclude that there is a path from PJ to PI of length k. Now, in this example, if an alive message from PI to P2 and P3, and this message contains 1 and 3 does not arrive on time to P2 or P3, they must consider another leader, but it's not that simple. Because, well, the question is why it's not that simple? Because from an alive message containing J and n-k, PI learns the following. The first thing is that PJ is a candidate to be the leader. And second, there is a path of k hops from PJ to itself. Remember that we assume that there is a spanning tree of diamond 880 channels, but what happens with the other edges? These edges can either be diamond 880 channels or not satisfy a property at all. So we need a mechanism for dealing with those paths. And in this case, for coping with ill paths, assuming that PJ will be the elect leader, PI can receive different hop bound values from forwarded messages. And every time a hop bound value does not arrive on time, there is a penalty that is increased. And now PI will wait for an alive message, J n-k, with n-k being the hop bound with the smallest penalty. Now, what happens if an elect leader fails? Eventually, the timer for all the hop bounds must expire, so everyone proposes itself as the leader and the algorithm starts over again. Now, we have the following bounds. On the message size, we have that on every alive message, we are sending only 2 integers, which are bound by n, meaning that we can encode the messages with log n bits. And on the time that takes to find a leader once the system is stable, with stable I mean that all the failures already happened and we have in all the timeouts reached the upper bound, order of d times delta, with d the diameter of the graph after all the failures. And delta is a constant that we can calculate with the constants of the channels, K and D, and T, the frequency with which the messages are sent on the live messages. Now, we run some some experiments, and our experiments verified that the convergence time is proportional to the diameter of the graph. Now, we proposed an implementation of omega in the unknown membership model. In this case, processes need to know each other first, and then we can use the previous algorithm, because remember that we need to send alive messages containing the proposal for the leader and a hop bound, and this hop bound is based on the n. Now, for this, every process sends its identity through its input channels, and every time a process knows a new name, it increases a hop bound, its local hop bound. And once a process confirms that a neighbor receives some information previously sent, it stops sending it. And the leader election algorithm remains the same, except for the penalties, because in this model, we assume that all the channels are diamond ADD. Now, everything sounds great, but remember that acknowledgement is not trivial, because let's not forget that we are working with diamond ADD channels. So it is not possible to know how much messages are needed to be sent to communicate something. Now, when a process P knows R for the first time, we will follow the following steps protocol for kind of a broadcast. P sends several times the pair R new to every neighbor Q. Now, as soon as Q receives the new name, it answers to P with the pair R ACK. When P receives this pair, R ACK from Q, it stops sending the R new pair, because Q already knows this information. And when Q realizes that this pair is not arriving from P, then it concludes that P received the acknowledge and will stop sending it. Now, something that I forgot to mention about this algorithm is that eventually we send only order of log. Our messages at the end are eventually of order of log n. Now, as conclusions, we present an implementation of Omega in an arbitrary network of diamond ADD channels with messages of order of log n. And we use the hop-down values for coding lightness information that allows the use of messages. And in the case of the unknown membership model, a mechanism that helps to deliver and acknowledge information. And this helps us to achieve, again, order of log n size of the bound on the size of the messages. And then something important that we did too is the performance analysis of Omega. And well, that will be all. Thank you very much for your attention.